So last video we looked at Maclaurin polynomials. This video we're going to look at Maclaurin series. I'm going to still lay out the basics, but if you're having trouble getting some of the ideas, look into the last video. I explained it a little bit more fully there. So Maclaurin series is just a series where the value and all derivatives equal those of a function at x equals 0. The x equals 0 part is what makes it Maclaurin. Now, writing that a little differently, that means that p of 0, the Maclaurin polynomial of 0, is going to equal f of 0. P prime of 0 is going to equal f prime of 0. P double prime of 0 is going to equal f double prime of 0. In general, the nth derivative of p evaluated at 0 equals the nth derivative of f evaluated at 0, and it continues forever. It does not stop like it did for Maclaurin polynomials. Now, before I jump into some examples, some things that you might want to keep in mind. So we remember that this Maclaurin series is going to be p of x equals a naught plus a1x plus a2x squared plus up to the general term a n x to the n, which can be written as the sum as n goes from 0 to infinity of a sub n x to the n. And the nth coefficient is going to be found by taking the nth derivative, where the 0th derivative, when I say that I mean the actual function, evaluated at 0 divided by n factorial. So this is a formula we will use a lot. Or you can consider that the nth term is going to be the nth derivative evaluated at 0 over n factorial times x to the n. So either way, you're finding these terms in the sequence. Now, a couple of things. First off, here are 3 series that you should probably just have memorized. They're useful, and if you have them memorized, you can actually do a lot of problems very easily. I'm going to give you these, and then in the next 3 slides, I'll go through and prove each of them, show you how we got there. But sine of x is going to equal x minus 1/6 x cubed plus 1/120th x to the 5th minus 1 over 5040 x to the 7th, and this keeps on going, which will equal the sum as n goes from 0 to infinity of, we only have odd powers of x, so I'm going to have x to the 2n plus 1, that's going to give me odd powers. It alternates, so I'm going to have a negative 1 to the n, and it's over odd factorials. This is 1 factorial, 3 factorial, 5 factorial, 7 factorial, so I will have 2n plus 1 factorial. So that is the Maclaurin series for sine. Cosine, we have 1 minus 1/2 x squared plus 1 over 24 x to the 4th minus 1 over 720 x to the 6th. And it's very similar, so you see that this is the sum as n goes from 0 to infinity I only have even powers of x, x to the 0, x to the 2nd, x to the 4th, x to the 6th. The next one would be x to the 8th. So I have x to the 2n. It alternates, so I have a -1 to the n. And I only have the even factorials. 0 factorial, 2 factorial, 4 factorial, 6 factorial. Next one would be 8 factorial, which is, let's see, 40,320. So that would be 2n factorial. And then the final important series here is e to the x, and that's just going to be 1 plus x plus 1/2 x squared plus 1/6 x cubed plus, it keeps on going. Now, on some of the AP problems, they say write the first 4 non-zero terms in the general term. I'll show it this way. So I just wrote the first 4 non-zero terms and then put ellipsis here. I do have the general term here, but if they say write the first 4 non-zero terms and then the general term, they want the ellipsis, then they want you to show that I'm adding on in general. Let's see, we have all the powers of x, so x to the n. I'm not alternating, so I do not need a -1 to the n. And I'm dividing by each of the factorials, so n factorial. And this is the way they'd want you to write the first 4 non-zero terms and the general term of this series. And that's, of course, equal to the sum as n goes from 0 to infinity of that general term, x to the n over n factorial. You can check if you're unclear whether you've got it. When you put it in 0, x to the 0 is 1, 0 factorial is 1, we get 1. When n is 1, x to the first is x, 1 factorial is 1, we get x. So it works. Okay, next 3 slides are going to be proving these. If you already know or if you believe, you can go on to some examples. But let's look at sine. So in sine, in order to find this, I'm going to just go through the process. Look at f of x, look at f prime of x, look at f double prime of x, look at the third derivative of x, look at the fourth derivative of x, look at the fifth derivative, and see what happens. Now, this should be enough to catch the pattern, okay? If it's not enough, you keep going till you see the pattern. So, the function is sine, the derivative is cosine, the derivative of that is negative sine, the derivative of that is negative cosine, the derivative of that is positive sine, and the derivative of that is positive cosine. And I'll show all of the steps again, this being the first one. In the next 2, I'll sort of skip along. So there should be sort of a dot, dot, dot going on here. It does continue. So I evaluate each of these at 0. The third derivative at 0. The fourth derivative at 0. And the fifth derivative. Evaluate at 0. Okay, sine of 0 is 0, cosine of 0 is 1. Negative sine of 0 is 0, negative cosine of 0 is -1. Sine of 0 is 0, cosine of 0 is 1. And then I get the coefficients by dividing by the n factorial. So a1, a2, a3, a4, and a5. I keep on forgetting to put the ellipsis because it doesn't stop at a5, it keeps going. So ellipsis there, ellipsis here. Okay, so I do 0 over 0 factorial. 0 factorial is 1, 0 over 1 is 0. 1 over 1 factorial, 1 factorial is 1, 1 divided by 1 is 1. 0 over 2 factorial, 2 factorial is 2, 0 divided by 2 is 0. Negative 1 divided by 3 factorial. 3 factorial is 6, so I get -1/6. 0 divided by 4 factorial. 4 factorial is 24. 0 divided by 24 is 0. And 1 divided by 5 factorial. 5 factorial is 120. 1 divided by 120 is 1/120th. And now you should probably see the series sort of coming out of here. So I have... All right, I'll just write it this way. Not just the power series, but sine of x. And it's sine of x equals because this converges everywhere. But we don't have a constant, but I have 1x I don't have an x squared, but I have a negative 1/6 x to the third. I don't have an x to the fourth, but I have a positive 1/120th x to the fifth. And you can see, okay, the derivative is going to go 0, 1, 0, negative 1, 0, 1, 0, negative 1. And I'm dividing by 1 factorial, 3 factorial, 5 factorial. I know the next one's going to be a negative 1 over 7 factorial x to the seventh. And in general, I'm going to have negative 1 to the n is going to alternate. The odd numbers, 2n plus 1 factorial, x to the 2n plus 1. And so that gets me to that series for sine. Now let's look and see what this series does. So here's the blue curve is sine. The red line is the first degree Maclaurin polynomial, so it's the linear approximation. And as I add on more terms, you can see when I add on the second term, it doesn't change anything because there is no squared term in the Maclaurin series for sine. But when I get to the third term, I get this. And as I add on more and more and more terms, it gets closer and closer to sine. Okay? And at a limit, when I get infinitely many terms, it will actually equal sine everywhere on the real number line. All right. So similar work for cosine. I'll reduce it down a little bit. So I need all of these. So f of x, f prime of x, f double prime of x, the third derivative of x, the fourth derivative of x. And this should be enough to see the pattern for this one. Again, keep on going to see the pattern. F is cosine. The derivative is negative sine. The derivative of that is negative cosine. The derivative of that is positive sine. And the derivative of that is positive cosine. And I'm not forgetting the ellipsis this time. I'm going to skip along, like the notation I used in the last video. So at x equals 0, cosine of 0 is 1, negative sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0, cosine of 0 is 1. And again, I'm going to skip along instead of writing out all these little bits and pieces. So I get 1 over 0 factorial. 0 factorial is 1. 1 divided by 1 is 1. 0 over 1 factorial. 1 factorial is 1. 0 divided by 1 is 0. Negative 1 over 2 factorial. 2 factorial is 2, so I get negative 1/2. 0 divided by 3 factorial. 3 factorial is 6, so I get 0. And 1 divided by 4 factorial. 4 factorial is 24, so I get 1 over 24. And this does continue, which gives me this series, or again, I can put, for this case, because it converges everywhere, cosine of x equals, I have a constant, I don't have an x term, I have negative 1/2 x squareds, I don't have any x cubes, I have positive 1 over 24 x to the fourth, and we can see it's alternating. The next term is going to be minus. I have 1 over 0 factorial, 1 over 2 factorial, 1 over 4 factorial. It's going to be 1 over 6 factorial, which is 1 over 720. And I have the even powers, x to the 0, x to the second, x to the fourth, x to the sixth. And that gets me to that general term we had where it's alternating, negative 1 to the n. I have even powers of x, x to the 2n. And I have the factorials of the even numbers, 2n factorial. And let's look at the graph and see what happens. So I'll change from sine to cosine. And this is the linear approximation of cosine. It's a horizontal line because there is no x term. As I add on more and more terms, you can see that it gets closer and closer to cosine, such that the limit, when I get to infinitely many terms, will be cosine everywhere on the number line, everywhere on the real numbers. Okay? Last sort of proof here, e to the x, which is one of my favorite functions to work with. So same thing, f of x, f prime of x, f double prime of x, and actually probably the third derivative is deep enough to see what's going on. Each of these is equal to e to the x. At x equals 0, each of these is equal to 1. Of course, we're moving on. It's not just that. And then, to get the coefficients, we divide by the n factorial, so a sub n. 1 divided by 0 factorial is 1. 1 divided by 1 factorial is 1. 1 divided by 2 factorial is 1/2. 1 divided by 3 factorial is 1/6. And we can see that our Maclaurin series e to the x equals constant 1, 1x, 1/2 x squared, 1/6 x cubed. And you can see, okay, I have each of the x's. They're not alternating, so I have an x to the n for the general. And I'll do it this way. I'm dividing by 0 factorial, 1 factorial, 2 factorial, 3 factorial, dividing by n factorial. So there is that series. And graphically, so I'm going to change this to e to the x. You gotta love GeoGebra. There's the linear approximation, and as I add more and more terms onto it, you can see that it gets better and better and better, further and further out, such that, since it converges everywhere, if I got the limit as we approach infinitely many terms, it will equal e to the x everywhere on the real numbers. So why do we care so much about these? And here's the reason. Find the Maclaurin series for this. And we did it for sine, cosine, and e to the x, but I really don't want to have to take all these derivatives, try to find a pattern, all that stuff. And here's what happens. If I recall from the series we just saw, I know that sine of x is equal to 1 minus x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7 over 50/40, so forth, so on. And actually, I'm going to do it this way. So that's going to equal that infinite sum as n goes from 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. We know that cosine was equal to 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720, so forth and so on, which was the sum as n goes from 0 to infinity of -1 to the n, x to the 2n divided by 2n factorial. But I don't have cosine x. I have cosine of x squared. So this is going to end up equaling, so I'm going to change this. So cosine of x squared is going to be the same thing, except everywhere I had an x, I'm replacing with an x squared. So I have 1 minus, I'll write like this, x squared squared over 2 plus x squared to the 4th over 24 minus x squared to the 6th over 720, which is going to be the sum as n goes from 0 to infinity of -1 to the n, x squared to the 2n, all over 2n factorial. But there's one thing I can sort of combine here, and that is x squared to the 2n. This is a power of a power, so I could rewrite this as the sum as n goes from 0 to infinity of -1 to the n, x, I get rid of those parentheses, x to the 4n all over 2n factorial. And that will be for x squared. And if I want to write this series, all I need to do now is just combine these. So I can either combine these terms, Or I can just combine these written out series. And that's what I'm going to do. So I'm going to say, okay, that lets me know that g of x is equal to this series. So I'll do that one in blue. The sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. Now, I could pull this straight into this sum, or I can leave it separate. I'm going to leave it separate. I don't think it makes much of a difference. Someone may have a care one way or the other. I don't. So minus because there's a minus sign here, this series. Negative 1 to the n, x to the 4n, all over 2n factorial. So if you know these, you can actually just skip to your answers right away. I wrote all stuff down, but you didn't need to write it all down. Unfortunately, there are still some problems, like on the AP test, where they won't let you get away with just using what you've memorized. So in here, this is the type of problem we would have there. And I'll go through the process. So we know that g of 0 is 1. I know that g prime of 0, this is that case where I want the nth derivative. This is the first derivative, means n is 1, so I put 1 in here. So I get 1 minus 1, which is 0, factorial, over 2 to the first, which is going to be 0 factorial is 1, 2 to the first is 2, I get 1 half. The second derivative, 2 minus 1 is 1, 2 to the second is 4, so I get 1/4. The third derivative, 3 minus 1 is 2, so I get 2 factorial over 2 cubed. 2 factorial is 2. 2 cubed is 8. 2 over 8 is 1/4. I continue this process. Let me show one more factorial here. It's a little bit hard to see. So the fourth derivative, evaluate 0, is going to be 3 factorial over 2 to the 4th. 3 factorial is 6. 2 to the 4th is going to give me 16. So this will give me 3/8. Now, we're going to go and get the terms. So the a sub n terms, all of them. Okay, divide this by 0 factorial, and I get 1. 0 factorial is 1. Divide 1/2 by 1 factorial, I get 1/2. Divide 1/4 by 2 factorial. 2 factorial is 2. 1/4 divided by 2 is 1/8, because the 2 goes to the denominator. Divide 1/4 by 3 factorial. 3 factorial is 6. So 1/4 divided by 6 is 1 over 24. And 3/8 divided by 4 factorial. 4 factorial is 24. 3/8 divided by 4 factorial. Well, let me do it this way. So I can have 3 over 8 times 24. The 3 and the 24 can reduce down some as 1/8, and I end up with 1 over 64. And it's like, okay, what's the pattern? We don't see this pattern going on. So here's the idea. Here's how I figure out what pattern this is. I see that I'm going to have p of x equals 1 plus 1/2 x plus 1/8 x squared. And you say, okay, I might have some ideas. Plus 1 over 24 x cubed plus 1 over 64 x to the 4th. Sometimes reducing these things down makes it harder to see the pattern. Okay? I'm going to sort of eliminate this from our list and just leave it in here because this might come from something different. But the rest of them, this was all found. This final thing was, I had a 0 factorial in the numerator. I had a 2 to the first in the denominator, and I had a 1 factorial in the denominator. This, I had a 1 factorial in the numerator. I had a 2 squared in the denominator, and then I had a 2 factorial in the denominator. This had a 2 factorial in the numerator. It had a 2 cubed in the denominator and a 3 factorial in the denominator. This had a 3 factorial in the numerator. It had a 2 to the fourth and a 4 factorial in the denominator. Now, here's the idea. In general, if I just look at this divided by n factorial is going to be my term. So I really have n minus 1 factorial in the numerator divided by 2 to the n times n factorial. The way factorials work is there's one extra term down here. So that's going to be 1 over 2 to the n times n. That's the general coefficient. That's where we get like this 64. 2 to the fourth is 16 times 4. Okay? So from here I can get the sum as n goes from, I'm going to go from 1 to infinity because I'm going to start with this term here. I can't start at 0 because this pattern does not hold for 0. This 0 down here would mean I'm dividing by 0 wouldn't work out. But if I start at 1, I'm good, and I can get this times x to the n, so x to the n over 2 to the n times n. And that is how I would get this series. So, trick to this, sometimes more simplification, getting these terms, actually makes it harder to see the trick that's going on. I hope that helped out. Feel free to comment below with any questions. And I'm going to put up a nice little video about e to the I theta.